Hello, everyone. This week's topic is going to be about a little bit about the control theory, some control basics, and also the introduction of the symbolic toolbox, how we can use it throughout the semester in this course. It's going to be mainly about these 3 points. One of them is using the symbolic toolbox to plot the root-locus plot. We are going to recall what the root-locus plot was for, how it was useful, how we can generate ourselves a root-locus plot using the symbolic toolbox, to look behind the scenes, what's really going on behind the R-locus command that we are familiar with. The second topic will be about the Bode graph. It's a frequency domain plot that we all might already know. We will be talking about the origins about this Bode graph, how to plot it, and again, what it is useful for. And the last topic of today will be the generation of the impulse response and ramp response using the step command that is already available in the control system toolbox without using Simulink or other stuff, because there's a quick trick here that we are going to recall about LTI systems. And then we are going to conclude the day. We are going to call the day off. Now, let's begin with the root-locus plot, what it is good for, and how we can generate our own root-locus plot. Now, I'm going to, well, let's call it TF, not R-locus. I'm going to create a transfer function that looks like this, for example. And we all know that we have this R-locus command, and we can just call it. And hopefully MATLAB will show us the root-locus of this transfer function here. Finally. Now, we have this root-locus plot in front of us. Do you remember what we were using the root-locus plot here? What can you say about this plot? What does it help us? How does it help us here? What can we conclude by looking at this root-locus plot, where the transfer function is given with line 3? So, any ideas? What can we learn from this graph here? You can ask your question in English or in Turkish. I'll translate it to the other language. So feel free to just answer.
Unstabil yere geçmiyor.
Şimdi unstabil yere geçmeyen şey nedir peki?
Yani kazanç.
Kazanç.
Sıfırdaki köklerinden sonsuza kadar
Hı.
gittiğinde unstabil bir yere gitmiyor. Hep stabil kalıyor.
Peki ney bu stabil kalan şey?
Yani sistem.
Sistem. Ama hangi sistem? Çünkü GS'nin kendisi zaten kararlılık analizine baktığımızda 1, 2, 3 katsayıları köklerini hesaplasak buluruz ve zaten kararlıdır. K'ya göre
Transfer
değişen şey ne?
fonksiyon, yani feedback aldıktan sonraki transfer fonksiyonu değil mi?
Evet.
Onun
Dolayısıyla
kararlı olması gerekiyor.
aslında bu gördüğümüz ekran doğrudan bir kontrolör ile ilgili bir ekran değil mi? Bir grafik ve kontrolörün bu katsayısı olan K dediğimiz sabit şey değiştiği zaman bu kontrolörün aslında neler yapabildiğine şahit oluyoruz kapalı çevrim transfer fonksiyonu olarak. Dolayısıyla arada kelimeler var ama tam anlamıyla ifade edeceğim zaten birazdan. Well, the first answer was that it doesn't cross the stability bound. It's not becoming unstable. Well, then I asked, what is not becoming unstable? Now, the answer was that if we have a feedback, then the gain from 0 to infinity doesn't bring up unstable poles, sort of. Now, of course, there were some keywords in this answer, but the exact way of defining the root-locus plot, or what it is showing us, is basically about a unit feedback. In this case, in our case, we have to know what the feedback is and what the feedback is good for. And then we can talk about the poles. Now, technically, all that we see here is the movement of the poles, of certain poles, versus a gain K. Now, what is the feedback and why is it useful? Let's talk about that first. This one is going to be the controller here. This is the plant or the system. And then we will have a summation point here. From there, we have the difference between certain two signals here. So now we call this part here, this input, the reference. And we're actually talking about the reference tracking problem. What this means is that in classical control, we will be talking about the reference tracking problem. We're trying to solve the reference tracking problem, which means that we are trying to command the system, and the system should behave like the input forces it to. So when we have an input reference R, what we expect ideally is that the output Y should be almost as identical as the input R. So Y, the signal output Y, should track the reference R. So basically, this is what we call the reference tracking problem here. Now, usually when we have no feedback at all, we might also come up with the same idea. We might also think that when we apply a certain input, the system should also obey the input and track it. This one here is called the open loop strategy, and this one is called basically the closed loop strategy. So let's therefore talk about the open loop strategy first. Now, as an engineer and as an assistant for many years of this course, I can right away tell you that, for example, using a coefficient 3 here as a certain sort of a controller or an open loop controller can help us out here. When I apply step input to the open loop strategy, where we have 3 as an input gain here, I can tell you that the output of the system will track the input eventually. But the keyword here is, of course, eventually, because it will not track it right away. Because we have dynamic systems, it takes systems some time to respond to inputs. And we can change the behavior with the open loop strategy to a certain degree. So I can show you or showcase you that if we have, for example, step 3 times GS, if I assign it a new figure here, like that, the output will look like the input eventually. So there we go. Now, since we are applying a unit step input, the magnitude of our input signal is 1, and our open loop strategy ends up being landing on this value 1. So it means that the transfer function between the input and the output is basically gain 1 here. But of course, this is just in the steady state of the system, where every transient settles down, everything has happened, and we are settling down. At this point, we call the system behavior steady state response, and from the beginning till the steady state, we call it the transient state. So in the transients, I have no power here, which I'm going to change in a minute, but we can see that it will eventually track the value 1. Now, I can also show you that not giving this value 1, not using the controller gain 3 here, we will see that even if I input a certain unit step to this system, the output eventually settles down at 0.333. Now, of course, I immediately calculated the steady state gain of the system and took the inverse. Why I did that is basically the systems under consideration throughout this course are called the linear time invariant systems. So it doesn't change over time. the response can change, but the model itself, the structure doesn't change over time. So therefore we call it time invariant. And therefore we can shift the response on the time axis, and it will just shift like we would expect it to, which is not possible for all systems. And it is linear in the sense that if I have input gain 1, output gain 1/3, I can just multiply everything with 3 and it will hold. So it means that if I have input 1 and output 1/3, if I input 3, I will get output 1. So therefore, this is called linear, and I can do that. Therefore, I can just find out what the steady state value of the given transfer function is, and then calculate it and take the inverse as a controller in the open loop as the open loop control strategy. Now, we can calculate this by looking for y infinity, which is basically the last, or what's it called, last value theorem, by taking the following limit as the final value theorem. Yeah, the final value theorem can help us out here because we're interested in the output in steady state. Here, infinity is not exactly infinity in time because that's just a concept. But what we mean is that there was sufficient amount of time passed and everything is in steady state now. So this is kind of a notation here. So y infinity using the final value theorem can be used like the following: s times gs times the input rs. Now, since our input is a unit step input, we can just input the Laplace representation of that, and we can immediately see that there's a pole zero cancellation here, or the values in the numerator and denominator cancel each other out, where we get basically the limit s times, or actually not even s times, we get the limit gs, where s tends to 0, like this. So when I plug in s equals 0 into the transfer function itself, I will immediately see that the ratio is 1/3. So once I've calculated this, I can just go ahead and say, okay, I'm just going to, there we go. I'm just going to take 3 times the input so that I will cancel out this gain here, and it will be identity. So I will get reference tracking here. So the question is then going to be the following: if I have such power, why will I need the feedback loop, which is represented here down here? Why will I need this? Well, you are actually relying too much on the transfer function model given in line 3. So you are relying on the mathematical model, and if for some reason something happens, or if you have an erroneous model here, which means that it could be 2.9, for example, and not exactly equal to 3, then your strategy will actually start to fail. But of course, in this case, it's not that big of a deal because it's 2.9 and then 3. That ratio will cancel each other out, and it will be roughly around 1. But there's also something called disturbance and noise. And first of all, you're just applying a 3 here, and you don't measure the output. Therefore, if you have certain disturbance that is acting on the system, it will shift your output immediately, and you will not get reference tracking. So, for example, if you have a vehicle, for example, and you have modeled your vehicle dynamics with this transfer function here, you're just pressing the gas pedal to a certain degree, and exactly 3 times the unit step. So it's going to be a certain angle here. And you're assuming that your car will reach a certain speed. Now, if you're going downhill or uphill, you're not looking at the output value. So you're not measuring your velocity. You don't know if you're faster than you expected or even slower than you expected. So therefore, it's just open loop strategy where you don't have measurements and you're just assuming stuff based on the model itself. So the real world conditions are not considered here because you don't have any idea, any clue about the real world conditions because you don't have measurement. So open loop strategy doesn't look good when you are trying to use such a thing, but in certain cases, this is still useful because you might have intelligent systems, adaptive systems, or systems in higher degrees, and you're just low components, low structure component is going to be an open loop controller. Sometimes you might get away with that, but most of the time you need measurement to evaluate the condition that you're in, and then you have to take a command. So therefore, the easiest thing to do is to get measurement. So in this case, you end up in a certain feedback loop because you're measuring the output Y, you're looking at the difference between the reference input that you're applying to the system and the system's output. You then have an idea if you're, for the car or vehicle example, if you're slower than you should be, or if you're faster than you should be, if you're going downhill or uphill, then you can evaluate that because you have an idea about it because you took measurement. And then the controller acts upon that measurement and applies a certain input to your system. So closed loop, therefore, this feedback loop here, or closed loop, is a better strategy. But then again, most of the systems in nature, in real-world applications, are stable on their own. So if you apply a certain limited energy, if you add energy to the system, it will consume that energy, and it will eventually end up being carrying out zero energy. So a kind of stability definition, a roughly stability definition that I gave here. But if you use a feedback loop, you might end up being designing an unstable closed loop here. That was not possible unless you were looking for helicopters or flight systems. Those are unstable by nature, or some pendulum or stuff like that. There are unstable systems in the real world. But most of the systems that we are considering in this course are about stable systems, and they are stable by nature. Now here you have to be careful by choosing the controller because you might end up in instability, and that is only your fault. If the system closed loop is unstable, then that's your fault. That's it. The system on its own is probably stable. Therefore, you have to take care about that. You need a mechanism, or maybe you need something, some tool to evaluate the stability of the system. And also what we're trying to do here is just we're not only considering the design of a controller, we also are interested in changing the behavior of the whole system. So here we're trying to act on the system, and here we're still trying the same, but the goal is also most of the time to have a certain behavior. For example, if I have a vehicle, it shouldn't it should obey the speed limits. It shouldn't be faster than the speed limit because that will end up in a ticket. So that's something like overshoot, and I don't want overshoot, or I want a reasonably amount of overshoot, like 10%, because that's the law. So that could be a consideration. And then I want to have, for example, minimum consuming vehicle. So my controller should optimize for energy, or it could be a speeding car, so it should optimize the time, it should minimize the time, so it should be a time optimal controller. So we have some sort of a behavior in our mind when we're designing a controller, and therefore we are trying to change the system's behavior in the closed loop. Now here, since I've used only a static gain, it was not possible to do that. But for example, I could do something like the following. I could come up with an open loop controller like 3 divided by, let's say, s plus 1. Let's see what we get then. Now you can see I eliminated, for example, the overshoot here. I could also improve on that. Let me I can slow down the settling time here. So it's quite fast. But what I can do is, for example, I can choose, I guess 0.1. No, it should be 10. I could choose this controller as an open loop controller, and I'll get like 40 seconds of settling time. Roughly 40 seconds. It takes more time, but it's slower. It could be used as a controller for certain systems. Now, why can I come up with such open loop controllers? Well, basically, you need the knowledge that we're going to give you in like 3 or 4 weeks from now on. So you have to have a good idea about poles and zeros and transfer functions, the controllers, basically all that stuff that we're going to cover in the laboratory for the upcoming 3 weeks. Like, yeah, almost. Now, the open loop control strategy is mostly about just changing the gain, maybe adding a pole or two to have a certain behavior. The best way of designing a controller, of course, is to take the inverse if the system is invertible and if the inverse of the system is also stable. Then you might look for the control with the inverse of the system open loop strategy. That's one of them. Which I've done with choosing 3 just by gain, or you can also take the dynamic part here. But the open loop strategy is not that important and common anyway, so we can just get rid of it. It's just to give you an idea, and since we will have disturbance in our systems, this doesn't make that much sense to use, but for very special cases, it's possible to opt for that. Now here, what we can do is we can look at the connection here. We have R. Since this is R minus Y, we will have an error E. And then the controller will generate basically a control input U, and the system response is going to be Y. Now, if you don't know the closed loop formula, what you can do is you can just write down the formulas here. Based on the connection, we know that E is equal to R minus Y. We know that U is Fs times E. We also know that Y is GSU. Now, combining these, for example, we could take this part here and use this equation here, plug it in, and we end up in E. So E is R minus Y, so plug that in too. Distribute GSFS times R minus GSFS. And this will be then Y plus GSFS Y equals GSFS R. Let's factor out Y. 1 plus FSGS. I can also interchange the variables like FSGS. It's the same since we're in SISO. And, well, we can find out what the transfer function between the output Y and the input R is going to be, namely Fs times GS, the whole thing divided into 1 plus FSGS. So if you don't know the formula, you can just look at the connection and write down some equations and you will work it out. Now, for the easiest controller in the closed loop or unit feedback loop that we have drawn here is basically the static controller or just a gain as a controller. So when we plug in Fs equals K, which is called also the proportional controller Kp or K, it's proportional because it is generating the control signal or the input to the system proportionally to the error at hand. So therefore, it's basically U equals K times E, so it's proportional. Therefore, we call it the proportional controller or P controller. We will be considering the PID controller in the future. So proportional, integral, and derivative parts will be combined into the PID controller. So you have to know the P-type controller quite well to understand the PID controller even better. So when we plug in this one here, what we get is basically K times CS divided by 1 plus K times CS. Now, since we have this formula, what we can do is, let me just convert it into a comment here. We can assume that NS divided by DS is our transfer function because it's going to be a simple fraction here. And when we plug this into, what we get here is going to be K times NS divided by DS, and then 1 plus K times NS divided by DS. So if we multiply everything with DS, we should get basically this as the closed loop transfer function here. Now, the denominator of this here is basically the characteristic polynomial, PCS, of the closed loop system, which is quite important for us. Because when we have a certain transfer function, we take the denominator and look at the roots of the denominator. If those roots are on the left half plane in the S domain, then we call it a stable system, a decaying system. The same goes for the closed loop transfer function TS. So we should take the characteristic polynomial or the denominator of it and check for its roots. If these roots are on the left half plane, then we are good to go because we have stable closed loop systems. If that's not the case, then the value that we have used for evaluating the roots is not usable because it's not stable. And then we also need to come up with a certain K value that alters the system behavior in such a way that the desired specifications are met. For example, overshoot should not happen, then that's one specification that we need to kind of hit. And then there's the settling time requirement, and we're going to try to come up with a K value that meets all the desired requirements and then also end up in a stable closed loop system here. So you can see that the association between the poles or roots of the closed loop and the gain and then the specifications that are given to us are linked to each other, but the link is not that easy and simple because we need basically more than just having a polynomial to try to do what we are trying to do here. This is also something that you should maybe recall from your previous lectures, because this has a special name and we call it the Root-locus equation here. The reason why we call this the Root-locus equation is basically the fact that we are using the p-type controller as a controller, and we are looking at the possible gain values and the roots of this polynomial when we are looking at the Root-locus plot. So this Root-locus plot has some gain values k in it, and then we see that the result of ds plus k times ns, the roots of this polynomial, are basically lying on these branches here on this plot. So it gives us a visualization of the link between the controller gain k of a p-type controller in a unit feedback setup and the poles of that closed loop transfer function. So this is quite important. When you have Root-locus, you're basically at the first step of designing a controller, the easiest controller, p-type controller. So that's already called the control system design, and this is why we start with the Root-locus plot here. And I can show you that, for example, when we take k equals 0, this will reduce down to 0 times ns plus ds equals 0. This term vanishes, and you get ds equals 0, where ds was the denominator of the open loop system. So it means that these are the open loop poles. If I solve it, then I will get the open loop poles like this. It's also possible to show you that if k is very, very big, or tends to infinity, in other words, then I can alter this a little bit. I'm just going to divide by k, because k is not 0. k is not infinity. I'm just dividing by k and then looking at the limit here. Since k tends to infinity, ds divided by k will tend to 0. So I'll get ns equals 0. And you might ask yourself why this can be done. Well, basically, let's assume that k is 10 to the power of 3. Then if you look at this equation, and if you're multiplying something with 10 to the power of 3, ds loses its significance. It's going to be very small, and it's going to be contributing so low amount of to the polynomial that basically ns will dominate its roots. In other words, you can use this strategy by dividing by k and then tending k to infinity and see that, in fact, the ds compared to k is going to be smaller and smaller, and it will eventually vanish, and you will get ns equals 0, which then gives us the open loop poles because open loop zeros, because it's the numerator of the open loop transfer function, so zeros. So therefore, when we are plotting a Root-locus plot, which, by the way, can be a positive Root-locus plot or a negative Root-locus plot, depending upon the sign of the gain that you're trying to come up with. In our case, we are looking at the positive one because we are looking for positive gains. We start with the open loop poles, and we end up in open loop zeros. Now, for such a system, you have 2 poles, but no zeros. Well, actually, you have zeros, but they're not finite zeros. We call these poles finite poles, and this one are infinite zeros because there should be zeros. And you might recall the fact that plotting a Root-locus plot goes like this. You look for the open loop poles, evaluate the poles, the zeros, and then look for the difference. And then you calculate, for example, the angle of asymptotes. And then maybe the intersection of asymptotes, and then you just evaluate the positivity between the path of the poles, and then try to come up with the Root-locus plot. You're trying to generate a Root-locus plot with these steps. Now, these steps are basically the theoretical, or is the theoretical algorithm to plot a Root-locus plot here. Now, the reason why we are talking about asymptotes is basically the infinite zeros. So in our Root-locus plot, you can see basically, let's close this one down. Now you can see that we don't have finite zeros, but one of them is here at j infinity, and the other one is minus j infinity. So they're trying to reach the infinite zeros here in this case. When we have a 0, you will see that one of the poles will tend to that 0, and the other one will be tending to an infinite 0 again. So here are the finite zeros and poles. And the asymptotes are basically the infinite zeros. Then you can calculate stuff like that and sketch a Root-locus here. Now, of course, what you also can do is you can just plug in some k values if you have a calculator, and then try to look at the roots of the resulting polynomial, and then try to place them on the S domain, which is basically also the Root-locus plot. So therefore, since we have MATLAB here, we are going to use the second method that I've mentioned here. Namely, we are going to plug in some k values and then end up in the characteristic polynomial of the closed loop, or we are going to mix the ds and ns with k here, and then we will plot the poles of the resulting poles, or the polynomial here. So actually, Root-locus plot is basically a controller design graphic where you can choose a controller for A, stabilization of the feedback loop, because you might end up in instability, and B, for a certain design criteria, you might be looking for a controller for a certain overshoot and settling time. Before we transition into basically into creating a Root-locus plot, I can also look at this Root-locus plot here and make some assumptions about the resulting controllers and also the closed loops. For example, I can assume that, or I can conclude that for this set up specifically this system and a positive gain k, the setting time will not change. It will be always 4 seconds and it will be constant, no matter what the gain k is. So that's one thing that I can say, TS is constant. And I'm going to show you that. And I can also assume that or conclude that, but just by looking at this root-locus plot, that when I increase the gain value, the overshoot or the oscillations of the step response will increase. So we will have more oscillating responses and the overshoot will increase. So let me first show you if it's the case. In order to look for that, I can just come up with certain k values. I can use a for loop, and I could just do something like this. I equals 1 up to, so this is I equals 1 up to length kvec. And the k value here is going to be kvec I. So I'm basically choosing the values here. Now, since I'm going to look at the TS values and also OS values, what I can do, so setting time and overshoot values, what I can do is I can just generate a vector of zeros. I'm pre-allocating the vector here by using the size kvec. I don't know if I've shown this already to you, but if not, I'm showing it here. You can do the following. If you are going to use one vector and generate other vectors, and if you are someone like me who likes to pre-allocate stuff here for performance, then you can just use the size function of the vector that you're going to create a copy of, and then the zeros function in order to create an empty kind of shell copy of the size of the kvec here. So these will be at same size, but I'm not just looking for the amounts of rows and columns, and I don't save them in intermediate variables. I'm just copying the size, pass it through the zeros function, and it will automatically get rid of it. If it's even a 4-dimensional, 5-dimensional complex structure, it will just copy it. So no matter what. And you can see the length kvec is important here because I'm going to go through each element of the vector here, kvec. I'm going to use this value. I can just use the feedback command here, where I provide k times kval times gs, comma 1 here. So if you don't want to use this, you can also use kval times gs divided by 1 plus kval times gs. So I'm just going to show you. But there's a slight difference, and therefore we like to use the feedback command. And the difference is, does it show it? So this is TS. So let me show you that. And this is the one when we use kval times gs divided by 1 plus kval times gs. Now, these might look different, but in fact, this is basically the same. And you can see if I convert it into ZPK, zero pole gain form, like this, you can see that there's a certain s squared plus 2s plus 3 in the numerator and denominator. They cancel each other out, and the result is going to be the same. But throughout these manipulations, you can end up in unstable polynomials being canceled out in the numerator and denominator, and that's something that is quite dangerous. Therefore, MATLAB doesn't carry out this operation on its own to give you the responsibility of canceling them. Therefore, most of the time, just use the feedback command, or you might also use minreal to look for minimum realization to get rid of the unnecessary pole zero cancellations, but that's not a good idea. So keep the feedback command in your mind and use that for feedback calculations. That's the safest way that you should take. So I can basically use the step info commands in order to acquire the information that I wanted to. So let's run this one here. And if you recall, from the first lecture. We've talked about this struct here. They were like the C programming language structs, and you are going to use, or you can use the dot operator to access basically the fields here. We have a key value pair here. So for the keys, you can use dot operator. So what I can do is I can use info.overshoot in order to get the overshoot value here. And then info.settling time, for example, to get the settling time value here. So let's do that. tsvec I should be info dot not overshoot, settling time. Settling time. And then osvec I equals info dot overshoot. There we go. Now let's re-enable this. And this should basically show us the result here. Let's create another figure, call hold on for stopping basically the plot command from erasing the previous stuff, and grid on to place a nice grid for readability purposes. Now CLF is for clear figure, and the reason why I use this basically line over and over again is the following. When I'm using a figure, I like to use multiple plot commands and plot calls for different plots, but I want them all to be visible. And if I don't provide this hold on setting here, then MATLAB's plot command will just erase all the previous graphical data and it will override it. I don't want that, and I want to prevent that from happening, so I use hold on. But before that, I'm clearing myself manually the figure. So from now on, everything is going to be plotted on top of each other. So that's kind of a thing that I like to do. You might do it differently. That's upon you. Let's assign it a color. Let's give it a line width. Let's also give it a display name. I like to use this display name because now this is called TS, for example, because when I open a legend here and I tell it to just show, I don't really care about the order of the legend now, because every name is attached to the plot itself, so it will show automatically the correct name for the correct plot. If you don't use this display name, you can also provide the names like this, but if you change the order, you have to update the legend, and I don't really like to do that. So, well, what we can do is we can give it X label, which is basically going to name the X-axis for us. And this is going to be K. And then Y label. Well, some data, I guess. And yeah, title could be like TS and OS versus K. So let's run the script. There we go. So now you can see that the settling time here is basically almost not changing. And the overshoot value is increasing. It starts with a circa 15%, 16%, and it's just increasing up to 35. And if I change the gain values, it'll change. So what I can do is I can just come up with even higher values. Why isn't it working? Now, there we go. I can give 10, 20, 40, I don't know, 200, stuff like that. Run it again. And we can see, hopefully, that the overshoot is just increasing and increasing. Of course, it's not a linear increase in that case, but still, if I increase K, it increases, and we can see that the setting time is kind of constant for the values here. So the question might be the following: how did we draw such a conclusion from this root-locus plot here? Well, basically, if you know, and you don't have to know them now, but you have to learn them in the upcoming weeks. If you know the settling time formula for a second order transfer function, you know that the real part of the poles determines basically the settling time of the system, and that's constant here. Therefore, it will not change and remain constant. That was the conclusion that I drew from this root-locus plot here. And basically it's 4 divided by this value here, so it's 4. Now the overshoot value here is determined by using the damping ratio, and we can basically see that when we go up on this branch, we have basically an increasing slope here. And this slope corresponds to a lower damping ratio value. And lower damping ratio means lower friction, therefore more oscillations and increment of the overshoot value. So that's basically the things that I've used to conclude this. But there are many other examples that we can give here where we can try to guess how the system is going to behave. Now, well, let's try to first of all plot this root-locus using MATLAB, and then I'm also going to show you what the zeta and omega n, or basically the damping ratio and the natural frequency, what they are and how we can plot them. Yeah, let's try to plot this root-locus plot on our own. Now we use this rlocusgs command, so I'm going to comment it out because we're not going to use that. We're going to use the symbolic toolbox here. Let us define the same transfer function, s squared plus 3 times s plus, actually 2 times s plus 3 here. Now the strategy actually remains almost the same here, because if you remember, we've talked about the fact that ns times k plus ds is going to be the characteristic polynomial, or the polynomial which we are going to be interested in. Now we need a certain k value, and we are going to plug in this k value here, and we are going to look at the roots of this polynomial, and we are going to plot them. So I have a k vector here, which is not the best k vector. So let me update it a little bit, because we need all the values here. So start from 0 with 0, 1 steps, let's say up to 0.2. I'm going to increase the upper bound in a minute. So we have this k vector here. We are going to get the k value. Now at this point, what I can do is, let me leave this one here maybe. So I'm going to just take this one here, use k-val instead of k, and look for the roots of this. Now, if you remember the last week, I guess I have talked about this symbolic toolbox. We can use the coefs command here in order to acquire the coefficients of this polynomial. And we have to use s and all because it was using a tree structure. And if there's something missing, it won't give us the coefficient of that as 0. It would just omit that. And for that reason, we would be mistaken when we use those coefficients. So we have to provide s, and we also have to provide all in order to fill out the missing coefficients with zeros and have the correct order of the coefficients of a polynomial here. So I'm going to save them into coef. Now, at this point, I have to also convert them into double, because in our polynomial, we have the symbolic variable s and k, but we have plugged in k already. So there's only going to be s, and when we have the coefficients of s, there will be no symbolic variable whatsoever in the coefficients. So I can safely convert them into double. Because when we don't convert them into double, it will give us symbolic results, and we don't really want that at the moment here. So now these are going to be the poles that I'm trying to plot, basically. Now, how can we plot these poles on a certain plot? Well, let's get rid of the legend here. The x-axis is going to be sigma, basically the real part, and the y-axis is going to be j omega, and this is going to be the root-locus. Root-locus plot. There we go. So the only thing that remains is to plot this. Now this is on the S domain, so we need the real part of it, of the poles here. And then we need the imaginary part of the poles. Maybe place a cross, use line width 2, and we should be good to go. Let's close this one down. Of course, we didn't use an SDS from num then. The numerator, denominator of GSS. We didn't decompose that. So it asks us what K is because this doesn't exist. There we go. Of course, it does exist, but we didn't basically define K. So what we can do is we can just define K and then open this in order to see what the characteristic polynomial looks like, which is PCS, which looks like this. Actually, K has a value, I guess. No. Oh, we're calculating, we're overriding that, so I should write down PCS. There we go. This is basically our PCS, and we're evaluating this polynomial for the values of K that we have here. And this is basically the result. Of course, we have only used some points, 3 of them to be exact. So if I increase this upper bound here, we end up in a better root-locus plot here, of course. Now, yeah, technically speaking, we should be starting at 0 and we should tend to infinity. But with this small step size here, I would not like to have 200 here because it would take too long to evaluate this root-locus plot. As you can see, it takes some time. To plot this root-locus plot more efficiently, what we could do is we could just use a different strategy. And instead of having this linear stepping strategy, which can also be written with using linspace, by the way. Now, when you use linspace, what you do is you give the starting point, the final point, and then the amount of points that you want to provide here. I guess this corresponds to 2001 points. If we look at the length of it, length is 2001. So if you provide this, this would be the equivalent of this definition here. But the advantage here is that you can give less points to define this vector here to increase the performance. So you're increasing the step size here, basically. But then again, this is not the best strategy. We can improve upon that. This is not bad, but we can switch to logarithmic spacing, which is log space. And we can use 10 to the power of -2, 10 to the power of 2 with, for example, 100 points. So this is a better, more efficient way of trying to do stuff because I can just increase it like 10 to the power of 3. And now I'm looking for 0.01 as a gain value. And also I have the value 1000 in my K vector. So it's a better approximation to have logarithmic spacing in the gain values here. So you can still argue that this is a root-locus plot, and I would agree with you. This is not a continuous root-locus plot as we are used to it. This is kind of a discrete plot and it kind of resembles the Root-locus plot. It's not exactly the Root-locus plot that we're looking for. So, and the reason behind that is that we're using a for loop, and we are just plotting the poles immediately as we have calculated them. Instead of doing this, to have a continuous plot here, what we can do is we can accumulate the results in vectors. And once we have calculated everything, we can then plot maybe the path of a pole on the Root-locus plot. Because what we do here is we end up in two poles here. When I look at poles, for example, the last calculated value of this variable looks like this. So we have this complex conjugate pole pair as a column vector, and we're basically placing some crosses where these are the locations. And that's it basically. A wiser choice would be to accumulate this into a matrix or vectors, and then pick one pole from the starting point for k0 up to k infinity. We should basically create the path or plot the path of the resulting branch of the Root-locus here. So we can do that by using, again, poles, but now it is going to be a two-dimensional matrix. And the way that I'm going to store this is basically column-wise. So each column should correspond to a certain k value, and I should stack them side by side. Therefore, the amount of rows that I would get in this poles variable would be equal to the order of the system, because the amount of poles will be determining the amount of branches or the path of a pole, basically. So I have to have two rows for this specific system, and as many columns as the k vector has elements, because I will be picking a k value. I will calculate this. This is already a column vector. I will just save it to the corresponding column, and I will then transition to the next k value and do it for that until I'm out of elements in the k vector here. So this is not going to be poles on its own. It will be all the rows, but the ith column here. So that way, when I calculate like this, if we look at poles like this, we can see that it is a very, very long matrix with 2 rows and 100 columns, because we have 100 different k values. So you can also see that conveniently, MATLAB did just store the positive conjugate values in the first row. So we can safely assume that this is basically this belongs to the same pole. It's moving like this. And the other one is basically the negative conjugate is basically on the second row. So what we can then do is we can just use basically poles, first row, all columns. Again, poles, first row, all columns. Give it a certain color, but not a marker anymore. And it will connect all these locations on the first row to create the Root-locus plot that we are trying to plot here. And you can see this is basically one branch of the Root-locus plot here. So I'm going to use, again, another for loop from I1 to 2. And I'm just going to use the ith row and all the columns, ith row, all the columns, without providing any color, because plot on its own chooses its color from its own color map. So there we go. We have 2 branches. We did mark the starting positions, and we can do that basically. We know that these, the first values are basically the ones that we're interested in. So we can, again, do the same, real, and then poles, and then all the rows, first column, basically. Imaginary part of the same pole pair. But I'm going to place in some black X's like this. And there we go. There we have basically marked the starting points or the open loop poles here. And we have the root-locus plot here. Now, when we are looking at the root-locus plot, this grid on does not really work for us because it doesn't give us any data about the root-locus plot here. Therefore, what we can do is we can change that grid because this one doesn't make sense. So let's disable this grid on here. Don't even use it here. But let's, instead of that, use the sgrid command, which is the MATLAB command that is already there. It uses the zeta and omega n values that we can plot here. So we can give it a vector of 0.1, 0.1, up to 0.9, like this, and then some omega n values here. It's better to show than explain, basically. So let me just change this into 2. So we have a better plot here. It's still quite too much, I guess. Let's decrease it a little bit more. Yeah, it's a little bit better, I guess. Yeah, and our system is not the best system here at hand. So yeah, our x-axis is actually messed up. So let's say x limit from -2 to 2 to maybe, yeah, there we go. That's way better here. Now, you see that the sgrid doesn't plot for the right half plane, for example. Then you can see that the zeta omega n pairs correspond to the left half plane. By definition, zeta should be something positive, omega n should be something positive. We call zeta the damping ratio, omega n the natural frequency, and the circles that you can see here, which don't really resemble circles for our case here, but I hope I'm going to improve on that, are the omega n values. And these slopes and lines are basically the zeta or damping ratio lines. Now you can see that our system starts with roughly 0.6 damping ratio. And when we increase the gain, we cross even lower zeta values. So zeta is decreasing. So I said that this corresponds to a friction for the pendulum, for example. And the lower the pendulum faces friction, the more oscillations you will get. And the more oscillations, the higher the overshoot is going to be. So that's the reason why overshoot is basically increasing. Zeta is decreasing when we increase the K value or the gain. Now, it doesn't really change the real part of our pole pairs, and they are all aligned on this line here, so it will not change the settling time. We will use zeta and omega n in our upcoming course weeks for the p-type controller design and for all this time domain specifications, and you will get used to them, hopefully. Now, we might also change the system a little bit. Now, let me basically get rid of that. So, by the way, I like to do something else now here. I like to calculate the coefficients of ds, s comma all, and I want to basically calculate the order of the system automatically. You can do this by obtaining the coefficient vector of the denominator of the open loop. And when you do that, you will have s to the power of n, s to the power of n minus 1, down to s to the power of 1, which are n elements. And then you will also have the constant term. So you will have n plus 1 coefficients for an nth order polynomial. Therefore, I'll take the length here and subtract 1. So for this second order polynomial, you can see that you have 3 coefficients, 1, 2, 3. So when you subtract 1, you will get 3 minus 1 equals 2, which is the order of the polynomial. So then I can use this n here, here, for example, and also here. And when I change the order of the system, I don't mind it anymore. So let's add another pole to the system. S plus, I don't know, 1. And then like this. I don't know if I use this anymore. And yep. Now, is it going to solve it, or is it going to cause some issues here? I don't know. Yeah. Now the problem is the following, and hopefully I can demonstrate it well. Let's have 5 values for all the rows. Now, it doesn't seem to happen here, but it should happen somewhere. Yeah, here's the problem. You can see that the ordering is messed up because when we were here, we had the real part or the real pole as the third one here. And here's somehow we have the complex pole pair in row 2 and 3, but the first one is basically the real pole now. So they switched order. And in order to prevent that, what we need to do is we need to basically sort these. When we calculate this, we should sort them with a certain sort criteria. So let's say help sort. And there we go. This one could be, for example, something that we can use here. It says that it's sorting according to real A. And if that's equal, then it will sort for the imaginary values here. So we could try this one here. If this doesn't work, we can just try ABS here. So we should say sort this one with the real values. Or if this doesn't work, we will use apps here. So we need to sort them to associate the right one with the right path. Ascent or descent, or. So we're going to provide comparison method. We didn't use the key here. So comparison method real. Let's try that out. So there we go. We solved the issue here. Now this is 10 is too much, of course. But this is also still too much. Let's keep it power of 2. There we go. This is a way better representation of a root-locus plot. Now here we have 3 poles. 2 of them tend to the right here, and one of them is basically tending to the left. Now we can calculate the asymptotes and stuff like that, and we will see 60 degrees and negative 60 degrees and 180 degrees as the asymptotes, because we have no finite zero, we have infinite zeros. So this one tries to match the asymptotes, this one, and this one tries also reach the infinite zero with the according asymptotes here. You can see that we have now circles which correspond to omega n values, natural frequency, and we are crossing them through these zeta lines here. And when we use basically this coordinate system, what we can do is we can just pick any point here. And for example, this point here, or even this one here, can be characterized with damping ratio 0.0, 0.1, 0.1, and natural frequency 2. So if we use 0.1 and 2 as values for damping ratio and natural frequency, you will end up with this pole pair here with its conjugate pair. And that's going to be important for the upcoming weeks. So let me also plot the actual Root-locus that is generated by the Root-locus command here. We didn't create GS, I guess. So when I define GS, and if the polynomial order is going up, like for this one example, for example, I like to use convolution here. And I provided the coefficients of the polynomials, and it will just carry out the operation that is necessary. What I mean by this is you have to multiply s plus 1 with this polynomial, and then order them with descending order, and then take the highest order 1 here, and you should get basically the coefficient vector here. But instead of doing that, this multiplication is basically convolution in coefficient space. So you can just take the convolution of individual polynomial coefficients, and it will give you the desired result here. So let's run this. Basically, we get basically the same Root-locus plot here. Now, we can also create the same S-grid here. So you don't really have to plot it on the one that you've calculated here. You can just use basically S-grid on this Root-locus, and it will be graphically more helpful in my opinion. Now, I want to say something to sum up this Root-locus discussion here. Now, sometimes in homeworks and stuff like that, I see something as follows. For example, here we have some assistance in terms of data, and sometimes our student tends to read these values for overshoot, for example, and damping, and then assumes that this damping and overshoot value characterizes the whole system here. So if you read something like overshoot is 61.3%, then what this graphic or Root-locus tool tries to tell you is that if the system consists only of this pole pair, then you would get this damping ratio, overshoot, and frequency. It doesn't belong to the whole system, because I can also click this branch here, and it will give us a total different overshoot and totally different time domain data here. And it doesn't actually correspond to the system's overshoot. If you're looking for the system's overshoot, you should use step info in order to calculate that. But in this case, what this tries to tell you is that if you have this damping ratio, which is correct for this pole pair here you can see that the damping ratio is 1. This damping ratio corresponds to 61.3% overshoot. But this doesn't mean that if I apply step response to the system, that I'll get overshoot 61.3%. So these are totally different things. If, of course, for this system, if we have a dominant pole placement, then we will talk about along this line. Something like that is along these lines, but we cannot conclude that. If the system is a second order system, then you're good to go. You can just use the overshoot value that is written on it, because there are only 2 poles. But other than that, for higher order systems, this Root-locus plot doesn't give you overshoot and cannot give you overshoot data here. It can just give you damping ratio frequency, natural frequency, because the Cartesian coordinate poles are converted into polar coordinate poles. What you see here is basically polar coordinates. If you take the square of the real part, square of the imaginary part, take the sum, take the square roots, or in other words, just the absolute value of the pole, you will get basically the natural frequency. And if you get basically the angle between these two values, the A tan value, and this will correspond to a certain slope, and you will get basically this value, the damping ratios here. So they have a correspondence here, and you can use zeta or omega n, zeta and omega n as a pair to locate the pole on the S domain, or you can use the sigma j omega or sigma omega values to look them up on the Cartesian coordinate. But those are two coordinate systems that we use most of the time to locate the pole or pole pair. So don't confuse that with the step info because it doesn't give you step info data. Now, I hope that we've learned what the Root-locus plot is all about, how we can plot it using a symbolic toolbox. Of course, you don't really have to use it because our locus gives you basically the poles and kvac when you use it like we use the step command. So you can just use rlocus.gs in order to obtain this data here. I'm just going to run this. You can see poles and k-vector is basically calculated. You don't really have to go through all this thing here. You can just use this one line here and get what you're looking for. And when you're trying to design a controller using the Root-locus, you have this numerical data written down. You don't really have to click and then try to locate it exactly on top of a value, because you can search for a value in these vectors or matrices, and you will get basically your response directly. So I would recommend you to try that out. So this was the first part of our discussion of today. Let us just straight away jump to the second part, which is the Bode graph. Now, Bode graph is a totally different tool that we use in frequency domain analysis and designs. And let me just define basically our transfer function here, 1 divided by s plus 1. And instead of looking for step responses and trying to design controllers, when we have a Bode graph, we are actually plugging in some input, or we are applying some input to the system. We observe the output, and the relation between input output is basically the Bode graph. But since this is a frequency domain approach or analysis or synthesis tool, we will have the sine wave, and the sine wave will have amplitude 1, frequency omega, and phase basically 0. Now we apply this to a system, and since our system, again, is an LTI system, linear time invariant system, what we observe in the output looks also like a sine wave. But it's not going to be the exact same sine wave. It will have a different amplitude than the input, and it will have a different theta value or phase value. And the transfer function itself is basically responsible for the difference in amplitude and difference in phase, since this is the only thing that exists here. And when we input something like sine omega t, if we don't change the source, if you know something about frequency, if you don't change the source, the frequency will not change. So our dynamical system GS, or transfer function GS, is not capable of changing the frequency of such inputs. So therefore, we will have the same frequency in the output, because the frequency depends upon the source. Therefore, the interesting fact is that we can directly conclude what the amplitude is, or what the amplitude change is going to be, and the phase change is going to be for a certain omega value. In fact, it is the amplitude of the transfer function, gj omega, and it will be the phase or the argument, gj omega. So this is quite nice because we can look at the Bode graph and then read some values out of it for a certain frequency, and we can conclude stuff about about that specific frequency. We can say that it will be amplified, it will be attenuated with a certain ratio, which will be the gain here, or the amplitude. And then we can also say that it will be shifted in this amount of phase value. So it's kind of nice to understand how the system behaves for each individual frequency for a given Bode graph or Bode plot. We can use the symbolic toolbox because this is basically a way of manipulating stuff here. And we can plug in s equals j omega. And this transitioning from, or 1i times omega in terms of MATLAB, this transitioning from S domain into the omega domain or frequency domain is nothing arbitrary. This is basically the transitioning from Laplace transform into Fourier transform, which is quite interesting if you ask me, because, well, Laplace transform is something that we use in control system theory, but the Fourier transform is more of a signal processing topic. And yeah, think about the fact that almost all signals in nature can be expressed in terms of sums of sine waves with different amplitudes and different phase values or frequencies. The Euler theorem is quite powerful here in understanding that the frequency way of viewing stuff is a whole different world, and it's quite interesting to know about this. Now, you can check the Laplace transform integral and the Fourier transform integral, and you will see that the only difference is basically if you plug in S equals j omega, it's basically going to be the same integral and same transform here. But keep in mind that S is a 2D domain where we have sigma plus j omega. So sigma plus j omega. So it's a 2D domain that we're talking about when we're talking about the S domain, whereas the Fourier domain is only on the j omega axis on its own because sigma is by nature equal to 0. So we don't really consider something that has sigma in it. We're just directly on the j omega axis, which is quite important for us if you think about stability. So when we plug in this value, which we can and which we should do maybe, j omega substitute GSS S equals 1i times omega. I'm literally doing this. Therefore, I need something called omega, which is going to be real by definition. I will end up in something like this. Now, this doesn't look that interesting. But again, we have something that was also available in the Root-locus discussion. We have a Cartesian coordinate output, which we are not really happy with. So we directly convert it into polar coordinates, and it makes more sense for us. If you take the absolute value of this, or if you calculate the real value and then the imaginary value, take the square, add them together, imaginary, and then take the whole thing square root, then you will end up in basically using the absolute value of g omega, which is the same. Or if we use a tan of imaginary part of g omega divided by real part of g omega, this is going to be basically angle of g omega. This is basically the same. So I'm going to go with the simpler expressions here, like this. And you can see the angle of this, and then the absolute value of this is kind of, again, some values depending on omega. Now, since angle is in radians, I can also convert it into degrees by using this ratio here. Now, of course, when we don't know what omega is, this doesn't make much sense. So what we can do, as it was the case for the Root-locus plot, we can just come up with a certain values. And I'm directly going to go with log space here. So let's have that. Let's have 4 different values. And let's use a for loop to cycle through each omega value here. Omega val is going to be omega vec I. Now we need to substitute g omega val instead of omega. And there we go. Now we can see these are symbolic expressions because we didn't convert them into double. Maybe we can get rid of that problem. There we go. Now we have some numerical values. For the first frequency, we have 0.995 and then minus 5.71 degrees. And for the next one, it goes on like this. And for the last one, which is going to be just 10, we have 0.09 and then minus 84.28. Now, these are basically the amplitudes and phase values, which I have basically talked about here when we choose each individual omega value in this omega vector here, 0.1, 0.46, 2.15, and 10. Of course, this is not really that helpful if we don't visualize that. So what we can do is we can create a figure. Now here I'm going to use subplot, since the Bode plot on its own is also something that is a subplot. I want to have 2 rows, 1 column, and the first one of this is going to be the following. Now we can have hold on. It's not going to be CLF because here when we use the figure itself, it's going to be a figure, but here when we use subplot, it's going to be an axis object, and I'm clearing the axis here. Hold on, maybe grid on, and then plot basically omega vec and maybe magnitude. Let's give it a blue value, line width 2. And then I need the phase vector here. It's going to be the second one. We will have phase. So again, instead of just calculating them, I'm just going to accumulate them and save them into a vector like this. This is magnitude, this is phase, like this. Now, therefore, magnitude should be a 0 vector of size omega vec, whatever the size of omega vec is, it's going to be the same size. Phase is going to be the same. What we can do is we can use X label to indicate that the x-axis is going to be omega, which is the common axis here. And yeah, we should be good to go. So this doesn't resemble a Bode plot. The first reason for that is that the omega vector values are not really that much. So if we increase the number of points here, we will have a better plot in a minute. There we go. Now, this doesn't still look like a Bode plot. And the reason for that is that if you look close to the x-axis, you can see that the step size is basically linear, whereas our vector is logarithmically spaced. And if you look at omega vec, you reach the number 10, whereas it's not linearly spaced, it's logarithmically spaced. So what you should do is you should just tell MATLAB to change the axis scale into log scale. If we do that, we will get a more convincing Bode plot in a minute. There we go. This looks more like it. Now you would immediately see that the gain values are not in decibels. And the reason for that is I didn't convert it into decibels. Yeah, because it's not really that important here. But throughout this course, we might use decibels, so you should know the definition. 20 log 10 is basically the formula for transitioning from magnitude to decibels. And the reason for that is, by the way, the following. Actually, it is 10 log 10 and then something squared. Let's say g omega squared. And the reason for that is it was used for the power of signals. And since we have the decibels and not bells, we have basically the 10 times factor here. And since the properties of logarithm, what we can do is instead of having square, we can just have 20 here and look directly at the gain value here. So the reason why we use 20 log 10 instead of 10 log 10 and then the square of magnitude is basically this one here. So log helps us out here. In MATLAB, if you provide log on its own, as we did here, it corresponds to the natural log. And if you give the base 10 here, log 10, then it's basically base 10 logarithm here. So, yeah, we can just take 20 log 10, 20 times log 10 of magnitude. This would be then the traditional Bode plot with 0 decibels because log 1 is 0. And then the factor drops, therefore we have negative decibels, etc. Now, if you know this transitioning here, you can just divide it by 20 and take the 10 to the power of that value, what the result is here, and then you can just convert it into gain. But let me stick with the gain values here because, yeah, it's better to explain. Now, yeah, we can do something extra here. We have obtained basically our Bode plot. What I'd like to do is I'd like to just create more axes here in order to showcase you that when I create another subplot here, we can combine 2 and 4. And here I want to show you a certain, I don't need X scale here, a certain signal with a given frequency. So for example, let's take omega val 1. Now I want to basically use LSIM y and t, LSIM with the transfer function itself, with the certain input and time vector. So we can create the time vector with a step size of 0.01 and then like 10 seconds. And then the input should be sine omega t. So omega val t in this case. And I'm going to apply this input. And then I want to plot it here. Ty line with 2, maybe also another color here, blue. And that's it basically. Yeah. We did mess up because we didn't define GS. There we go. There we go. Now maybe we should increase the time a little bit, like 40 seconds, 50 seconds. We have grid on, okay. There we go. Now I want to save this subplot to AX1, and the way you can do that is basically AX1 equals GCA, where we also use GCA here for set and get. This is not going to be that important for the upcoming one or upcoming lessons, so you just can copy and paste it and never think about it. Here we use AX2. GCA stands for get current axis, by the way. Since we've created subplots here, it will get the current axis, which is subplot this one here. And if you call it here, it will be this subplot here. And you can also call it here to get the handle of the third subplot here. So the nice thing about this is you can then mix the ordering, and you don't really have to care about basically which order it was. You can just then provide it the handle, and it will just plot on the one where it should be. Now, the reason why I did this is because I can do the following. I know what the omega vector here is. So I can search for the minimum value of the following in order to look up what the gain and phase value on the Bode plot is. So omega vec minus omega val, and the absolute value of this, if I minimize the absolute value between these two, I can find out the value and index. I'm not really interested in the value because ideally this should be 0. I'm looking for the magnitude index and phase index here. And in fact, I can do a plot omega vec index, comma magnitude index, like this. Now this belongs to AX1, this belongs to AX2. Let's give it a red color, for example, red square, a line width of 2 for visibility. Again here on a different plot, maybe I can also change this into red to have color association here. There we go. Now we can see that this point on the Root-locus plot, because omega val is equal to 1, on the Bode plot, I'm sorry, has this value here, which is roughly 0.71. And you can see that the magnitude in steady state of the sine wave is again the same. We can also plot the input here. So maybe let's do that. So this is U. This is actually blue, and then we have U here. So you can see there's a little attenuation, which is expected due to the Bode plot here, because the lower the frequency, the better this transfer function just passes and doesn't attenuate. And the higher the frequency, at this point, actually, we're almost at the corner frequency. If this would have been a filter, we would then say that this part is basically rejected, this part passes through this filter. So that's kind of the business that we get from this system here. The system behaves like a low-pass filter. Therefore, what we can say is for slow behaving references in the input of the system, we can track them. But for higher frequencies, that's not going to be the case. What we in fact can do for the purpose of simulating the noise here, we can create a random vector with size t, and then manipulate it a little bit in terms of mean value. And yeah, we can also assign it a certain power here. And what we can do is we can add this to our input. So U plus omega, and then look at the output, at the result. You can see, even though our blue one, which is the input, has high noise in it, the frequency of these noises is quite high, and we have a very low pass filter that rejects basically those types of signals. We can immediately see that our signal is quite clean when we have this noisy input. Even though we have this noisy input, we have an almost ideal sine wave that doesn't get affected by this noise here. Now, this wouldn't be the case if this transfer function would change a little bit. For example, if we have 0.01 times s, like this. Change it a little bit. There we go. Now we have also noise passing through the system, because the corner frequency did increase, so our filter does not reject that many frequencies now. It has essentially some up to 100 radians per second. And if you convert it using 2 pi f, you can also get the frequency in terms of hertz. And you can see that, yeah, well, basically this system doesn't attenuate the noises that much, whereas the previous system was quite a better design in terms of noise attenuation. You can see, even though some attenuation is going on, it's not ideal. And yeah, we would like to maybe reject it a little bit more, or we are happy with this. I don't know, it depends upon the application. But you can see that the Bode plot quite helps us out in understanding what is going on, how the system behaves. And this is quite important because this is a whole different picture, and we can basically conclude stuff about the system, and it helps us out in understanding and maybe perhaps also designing controllers using Bode plots. Now, this was basically the second part. The last part is not that will not take that long, so let's get to it. Now here I just want to remind you of an important extension of the systems that we are interested in, namely the system is LTI, so linear time invariant is quite an important and restrictive in terms of transfer functions or models in the nature, and it has an important property. Now, the third task for today was to plot the impulse, step, and ramp response. And yeah, we can already use step GS. If I define a certain GS like this, we can use step in order to get the response here. So YSTS, for example. Now, I would like to create a figure, and with subplot 3 rows, 1 column, the first one of this, hold on, grid on, and maybe, yeah, Y label, in this case, impulse. Let's use X1 here. This will be the second one, the third one, the second one, the third one. This is going to be the step response. This is going to be the ramp response. And yeah, of course, we can also have the X label. Which is time. There we go. Now, I would like to quickly get these responses using the step function here. And yeah, since our system is linear, when we have x1 as an input to our system, and it gives us y1, if we have x2 as an input and it gives us y2, the combination a times x1 plus b times x2 should give us, you guessed it, a times y1 plus b times y2. This is called linearity. So therefore, we can just directly use superposition upon the system and then just sum them up to see what's really going on if we have a more complex input because of this property. Now, there's also a different property that we sometimes don't remember, and that one is basically if we take the, for example, derivative, so d divided by dt, x gs also carries out the operation d dt times y. And this goes also for the integral. So if we integrate x, the output will also be integrated. And the way that we can utilize this is exactly here, where we have the step type input and we want to obtain the impulse or ramp response. So we know, or we should know, that the integral of the step response is basically the ramp response. So we can just add an integrator to the system. So add an integrator to the system. 1 divided by S. We should get the ramp response. If we add a derivative to the system, so what I'm basically doing is I'm basically including 1 divided by S to the system so that the input's integral is applied to the system so that we get the integral of the output. I can do the same for this derivative here, which is directly going to be S. So I'm going to place S here, and we will get basically S times that and Y divided by S. If Y was the response of a step type input, S times Y should be basically the impulse response, and Y divided by S should be the ramp response. So let's see if it works in terms of the visuals. Now we can also get the impulse response by placing a derivative or an S term. So yeah, I could just take this here and we could share the time vectors here. Now we're going to plot ti, comma yi with blue and then line with 2. This is going to be ax1, ax2, ts, ys, yr, tr, x3. So since this is the ramp response, what I can do is I can use tr, tr, and k in order to basically show the ramp input. Here I can just use ts times once, actually just once times once size ts. So I'm just creating a vector of ones here because unit step. And let's have that. I'd prefer not to visualize the impulse type input because it would be 1 or infinity at t equals 0 and then 0 for all other time instances. Oh, this should be K3. Q3. And there we go. We have the ramp response, the step response, and the impulse response. And I didn't need to go ahead and open up a Simulink and then drop down the derivative or the right source for impulse and ramp and etc. I just utilize the fact that if I take the derivative of the input, the system's output will be the derivative of the output. Or if I take the integral of the input and apply it to the system, if the system is LTI, the output would also be integrated. So you can just add an S or 1 divided by S in order to switch from step response to impulse or ramp response. Of course, you can also add 1 divided by S square in order to have parabolic type inputs and examine the output of that. And you can go on like that. But yeah, these are quite sufficient in my opinion here. So this one was, again, something interesting about LTI systems. Now, in the notes, you will see almost the same applications. Here, we have a better explanation about how zeta and omega n relates to the poles of a second order system. We will be talking about this. And yeah, for the Bode graph example, the second part of today's discussion, in the notes, I've used basically a bandpass filter with a certain corner frequency and bandwidth, and here are the definitions. I then obtained the transfer function, and I have given the discussion based on this filter here because it makes it obvious that we have a center frequency of 100 hertz, and we're trying to have a certain quality factor, which is also relating to the bandwidth here. And the aim of a bandpass filter is basically to suppress all the other frequencies other than the central frequency that we are trying to bandpass, basically. And yeah, you can see that the Bode plot generation kind of shows us that this is in fact the response here. You can see here we have 1, and everything else than that is kind of attenuated. We also get basically a more detailed explanation on how this works when we have an equivalent transfer function that corresponds to step type inputs. But when we are trying to use the step function for unit ramp or unit impulse response, then we have to have this little operation, the algebraic operation here. But if you want to memorize it, you're just adding s in order to take the derivative. Step derivative is basically impulse. The integral of step is going to be ramp response, and that's the only thing that you should need to create this plot here. So this is about it for this week. We have used the symbolic toolbox throughout the day. We have talked about the root-locus, the Bode plot, and some other stuff about simulation. But next week we will be more controller design centric, and we will be talking about the p-type controller in much more detail. Therefore, it was necessary to address the root-locus plot on its own. Yeah, that is basically it for this week.